Okay, so got this cute cartoon. Sorry to bother you, ma'am. We sent out 1,000,000 offers for magazine subscriptions, and you were one of the 20,000 who was supposed to subscribe. So we actually will be looking at expected values for binomial distributions, and we're going to also introduce one more distribution, geometric, which, good news, not as complicated as the binomial. All right, so let's go back to the binomial distribution. Let's say you flip a coin 100 times. How many heads would you expect? So if it's a fair coin, you would expect 50 heads, right? And that's what the distribution looks like. Now, if the coin is unfair and lands on heads only 20% of the time, how many would you expect? 20, right? So your peak would be there at 20 instead of at 50. Now let's say another coin lands on heads 90% of the time. How many heads would you expect for that one? 90. And it would be kind of distributed over to the right like so. Okay, so this leads us to our formula for expected value. Expected value is just the number of trials times the probability of success on each trial. So now, and you can also see one thing we're going to get to, if these are a lot of flips, and these distributions look approximately normal. So determine which graph below goes with each of the following values. So 0.2 is actually for the left graph, all right? And if you look at it, and this is only a few trials, all right, 10 of them, and it's skewed to the right. If the middle one is 0.5, and that's roughly symmetric, and the right one is a 0.9, and that is skewed left. So you'll notice before I had 0.2 and 0.9, and those were not skewed. Those were roughly symmetric, approximately normal. How do we know when it goes from skewed to not skewed? Well, low and high values of p can be symmetric if the sample size n is large enough. So if np is less than or equal to 10, then it's not normal and it's skewed to the right. If n times q, where q is 1 minus p, is less than or equal to 10, then it's not normal and it's skewed to the left. So for these distributions, we would not use a normal approximation. But if we do meet the condition, if we're greater than 10, then we can use a normal model. All right, but if we use the normal model, we need a way to calculate standard deviation. And for binomial distributions, this is it. N times p, square root of n times p times q, or remember, q is 1 minus p. And in fact, on your math chart, I've used q a lot of times. Some books use q. When we say q, we mean 1 minus p. So here I ask you to determine n, p, and q. N is 50, p is 1/4 or 0.25, and then 1 minus p is 0.75. Is the distribution left skewed, right skewed, or symmetric? Well, we'll calculate n times p. We get 12.5, so that's higher. We calculate n times 1 minus p, and we get 37.5, so we met the condition for it to be symmetric. So what score would we expect on the test? We just do n times p, 50 times 1/4, and get 12.5. And what's the standard deviation? We plug in, and we get 3.06 roughly. Let's look at another example where a student rolls a 4-sided die 100 times and counts the number of times they roll a 1. What is the expected value in standard deviation for the number of times you get a 1? So we need n, we need p, and we need 1 minus p. So expected value is just n times p, in this case 25. Our standard deviation is square root of n times p times 1 minus p, or in this case about 4.33. And if we draw a rough distribution, you can see it's centered about 25. And yeah, it's about, if you go 6 standard deviations, about 24, 25 wide. All right. So we know anything over here would probably be pretty darn unusual. And that brings us up to our next topic. How do we decide if something is unusual? Well, it was kind of just the rule of thumb, and it was decided by the godfather of statistics. And he said, you know, if it's less than 5% probability of getting something, we say it's unusual or unexpected. All right. Don't know why he didn't pick 4%. He settled for 5%. So that tends to be our rule. So would it be unusual to roll a 1 on the dice 40 times out of 100? So we're going to actually look at 40 or more. And you can see that if I do the probability, I'm just going to do it quickly with technology. Normal CDF, the lower is 40, the upper is infinity. The mean is 25, and the standard deviation is 4.33. So I get 0.0003, which is 0.03%. Yes, that's unusual. That's a very low probability. So you suspect the die is loaded and favors a 1. How many 1s would you have to roll out of 100 to say it is unusual? So if it favors a 1, that's on the high end, right? So I get the z-score for 95% is below, 5% is above. And then I substitute in and solve for the value. So I get that x is 32.12. So anything higher than 32 would imply that maybe the die is loaded. All right. By the way, we'll go ahead and calculate for lower than 32 for a lower value as well. So here we go. I did inverse norm of 0.05 is negative 1.645. And if you substitute in, you see that a low value, anything like 17 and lower, would be considered really unusual as well. So results greater than 32 or less than 18 would be considered unusual.